Hey guys, today I want to talk about the reconstruction of a two-dimensional object using its shadows. This had been on my mind since I did the first video about inverse problems, and there I stated that this is possible to do so. And the question is, how can you do this exactly? In this video I will show you a very naive and very simple approach how to do this and how to implement this into MATLAB if you want to. So let's start. As usually, let's start with making some assumptions. Number one, we want the light to travel from the left to the right in a parallel manner to the x-axis until it gets stopped by some obstacle or it reaches the screen. On the screen, this is now assumption number two, there is only full light or there is absolutely no light. So we deal only in absolutes. And this is now combined with assumptions number three, there is no flare or reflection effects. Because these effects would make the modeling process and the derivation process way more complicated. And it's not needed to understand what's going on here. The object itself is now rotated around the origin in the spatial plane. And of course, for different rotation angles, we will observe different shadows on the screen. Here you can see the rotated object and its projected shadow for, let's start with a rectangle. And for every rotation angle, we can combine the shadow on the screen into a so-called rotation shadow tuple. This is posted here or shown here on the right side in the accumulated shadow. For a rectangle or for a square, you can maybe guess how this rotation shadow tuple may look like. But let's go to a real rectangle. And you can see here, the result is looks, of course, different from the one from a square, but it's not so intuitive. And things get more complicated if we look at, for instance, two squares rotating. And you can see here we have a hole in the middle in the rotation shadow tuple, and this is, of course, not very intuitive. And things get even more complicated if we start looking into the rotation of non-convex objects. Okay, fair enough, those two squares, they had also been non-convex, but this L-shaped form here is, of course, what I call really non-convex. You know what I mean. And the outcome here is absolutely non-predictable. And in the next case, we will show how we can formulate this rotation shadow tuple, how we can implement this into a mathematical framework and how we can tackle this using numerical methods. There is, however, a short disclaimer. I know that the formulation I will show you in the next couple of minutes is, let's put it that way, there exist way more efficient formulations out there, but for me, this is the very naive approach to formulate such a problem. And if you're more familiar with such inverse problems or such mathematics, and I know there exist efficient and nicer formulations out there, but this is just for a quick start, you know. With this short disclaimer in our head, let's start giving some objects some names. Our object is called O, and the rotation angular is called phi. And if the object is rotated around the angular phi, this object is called O of phi. This, of course, is now a subset in our space R2. And we can now formalize the shadow on the screen using the light traveling from left to the right in the following way. Imagine a light beam going from left to the right, parallel to the x-axis. Either the light hits the object, then there is zero light, or in other words, the shadow is 1, or the light beam hits the screen, meaning there is no shadow or there is full light. Remember, we only deal in absolutes. And in a formal way, this means if we find and point inside our object O on the light beam going from left to right, if this is now object O, means there is no light on the screen or there is full shadow. This can now be combined into our forward function, which generates for any given object the rotation shadow tuple in the following way. We start in the power set of R2, meaning any given subset of our space R2 is now mapped into any given subset of the space 0 to 2 pi times R. So 0 to 2 pi is of course our rotation angular, and our space R is our screen. And the tuple we are looking at here is the combination of our rotation angular phi and its shadow on the screen if we use the rotated object O applied to phi. This is now of course a subset or an element of our power set of this power set here. This is a way to formalize our forward function which we now want to minimize. So this is now our minimization problem here. Z is our given rotation shadow tuple, and we want to minimize our function f over the power set of R2. This is exactly here where the problems start. We have to use power set in this formulation, and how do we deal with the spaces? They're quite nasty to deal with. But there's a solution, of course. We just discretize them and work with the discretized version. First, start with some assumptions. We assume that our object O lies within this unit square, and not only the object lies within the unit square, also for every rotated object, so for all rotation angular phi, O applied to phi lies within this unit square. Now we distribute this unit square, or we equally distribute this unit square, this is important, into n times n points. Any spatial variables are called xi and yj. With this distribution at hand, we now can approximate our object O, which is a subset of R2 or an element of its power set, as an element of Rn times n, basically as a matrix, via the following definition. If our spatial coordinates xi and yj lies within our object O, then the element of this matrix at the position I and j is 1 or 0 otherwise. And as I just note, you can see it here, the exact values of this discretization are not that important because they are uniquely defined using the unit square and this word equally distributed. So this now gives a more convenient handling description of our element O. How does such a matrix look like? Well, you can see them here for different discretization levels. So this is the matrix you can see here of a simple rectangular for n equal 1000. Well, we have 200,000 non-zero elements, and if we would use the spatial discretization, of course, this matrix here gets coarser and coarser. This idea carries over to our rotation shadow tuple, which is an element of the power set you can see here. And in a very similar way, this can be approximated as an element of the space Rm times Rn. And here we are splitting the domain of our rotation angular from 0 to 2 pi into m equally distributed points phi I, which of course, well, the discretization is this Rm here. Using these techniques, we can now formulate the discretized version of our forward problem. Basically, we have to introduce a modified shadow function, which you can see here. This is a straightforward implementation or adaptation of our continuous function. And you can see here in this function fd, there is no power set involved here, just spaces we can deal with. So Rn times n, this is a space we can handle, and Rm times Rn, well, it's basically the same here. So now we have reduced the problem with the power set to problems where we can handle the spaces. And we now aim at minimizing this discretized function here. And as you can see here, it's very similar. The only major difference is that our power set is replaced by the space Rn times n. And of course, this evaluation of this function, well, this is now straightforward. This can be done in a very cheap manner. And this is as we can do it in a very cheap manner, this gives rise to the implementation or to the we can apply numerical methods to this. The easiest method is of course the gradient descent, and we want to apply it. However, before we apply it, we want to introduce the mapping M, which only maps the space Rn times n to the space Rn to the power of 2. This makes things easier, we will see in a moment, because it's easier to deal with the space Rn than with the space Rn times n. Introducing this method M into our optimization problem, we can rewrite this in the following form, and you can see that we are now searching, instead of searching for O into the space Rn times n, we are basically looking for X in the space Rn. And this is more easier to handle if you want to implement this into MATLAB. What do we have to do to apply the gradient descent? Of course, we have to calculate the gradient. The gradient, however, is not analytically available, so we have to approximate it. And the elements of the gradient can be approximated by the central difference. You can see it here. EI is the standard basis of the space Rn2. And you can see if we have to deal with the space Rn times n, well, we had to deal with two indices here, and this formulation using this mapping M makes things easier. Since we do not have any better ideas, we start with the 0 as initial starting vector, and we use a constant step size. You can see in these 2 points here there's a lot of space for improvement. However, let's talk about number 3. In the beginning, we stated that our object consists only of 1 out of 0. However, if we apply this gradient descent, we will obtain all numerical values. And this makes things harder to visualize. So we set the values of fd to be 0 if its absolute value is below 0.1, just for visualization. Okay? This will makes easier to visualize things and see, oh, our algorithm is actually working. You will see this in a moment. So let's start with the numerical results. We start with the rectangular, of always see them in the beginning, and what you can see here is the first 100 iteration of the gradient descent, and the desired shadow and the reconstructed shadow, as well as the desired object and the reconstructed object. And in addition, the evaluation of our function f. As you can see, as expected, the function values of f are decreasing, while the reconstructed object is getting closer and closer to the desired object. Keep in mind that every element which is below 0.1 is set to be 0, and it's oppressed in this visualization here, right? Keep this in mind. That's why I stated this will help us in the visualization. So for this example, this seems to be working out fine. Even for the non-convex case, for the two squares, we see that we have quite good conversion, at least from an optical perspective. So what happens if you go to the L-shaped form? For the L-shaped form, you can see it here, things are getting more trickier. We cannot expect to reconstruct the L-shaped form because this is a non-convex object, and if you just imagine there's no way you can reconstruct this. But the algorithm itself trying to recreate this triangle, which can be interpreted as a convex hull of this L-shaped form. But even in that case, the algorithm is getting closer to the best possible result. Now we are at the end of this small video, and it's time for a short summary. We have seen that we can perform a quite good reconstruction using very easy techniques. However, but this is due to the structure of the problem, we cannot reconstruct non-convex structures. They are hard or even impossible to recover. And I did not mention this, our approach has a very bad scaling when it comes to numerical effort. That's why I mentioned the disclaimer in the beginning. There exist way more efficient algorithms out there, but for the understanding how to model such a more complex optimization problem, this is a quite good scenario. So thank you guys, and have a good time.